All right, folks. Translations. Translations. Folks, the word translation and transformation are kind of the same. They're talking about the same thing. They're always referring back to that quadratic y equals x squared. It's that parent quadratic. It's that basic one. It's the one we always kind of refer to. So it says here, consider this quadratic here. Y equals x squared minus 2. It says make a table of values between -3 and +3. So here's our table of values already set up for us. And we're thinking, okay, y equals x squared minus 2. And what we're going to do is we're going to substitute the values of x inside that little blank there and come up with some new coordinates. So before actually we get into that, let's remember what y equals x squared looks like. This is y equals x squared. If it'll let us see it, yeah. Vertex at 0, 0. And notice how we go up, over 1, up 1, over 1, up 1, 2, 3. The next one would be over 1, up 5, but it's hard to see here unless you're counting by ones. Okay, over 1, up 1, 2, 3, 4, 5. And then we see the step pattern there. That's y equals x squared. And that's what we're kind of looking at almost always. This one's y equals x squared minus 2. So when we plug these values into our calculator, plug in -3. -3 squared is +9 minus 2, +7. Okay. -2 squared is 4 minus 2 is 2. -1 squared is 1 minus 2 is -1. 0 squared is 0 minus 2 is -2. And 1 squared minus 2, -1. 2 squared minus 2 is 2. 3 squared minus 2 is 7. So this is the graph of y equals x squared minus 2. We made the table of values. Start at the vertex and calculate. Okay, we got to graph this thing. So -3, +7. -3, +7. Okay, -2, +2. Alrighty. -1, -1. 0, -2. 1, -1. 2, 2. 3, 7. And we got this one. I'm going to try my best to draw on a smooth curve. Like that. Huh. What do you notice? If we're going to compare this to y equals x squared, what do you notice? It's not 0, 0. In fact, if you were to explain this to like a younger sibling, you say the vertex was here, and now, where did it go? If you were to explain this to like a kid in like grade 4, what would you say about the vertex? What's that? It went down 2 spots. 1, 2, right? That's all that happened to the vertex. It says here, starting at the vertex, calculate the step pattern. Okay, here we go. We're going to do it in green. Over 1, up 1. Over 1, 1, 2, 3, up 3. Over 1, 1, 2, 3, 4, 5. Step pattern. Did it change from the original y equals x squared? No, it stayed the exact same. So I'll say it's 1, 3, and 5. What do you notice from the original step pattern of y equals x squared to the step pattern of y equals x squared minus 2? It's the same. Step pattern did not change. Now here's the only thing that kind of did change. And we noticed that it was the vertex. So it says, what do you notice about the vertex of y equals x squared versus the vertex of y equals x squared minus 2? Well, in y equals x squared, the vertex is 0, 0. Yes? But in our quadratic, y equals x squared minus 2, the vertex is 0, comma, -2. Interesting. How about this? Actually, before we even move on here, why do you think the step pattern was not effective at all? Because look, our step pattern is 1, 3, 5. The step pattern of y equals x squared is also 1, 3, 5. They're the exact same y. The a value is the same. I mean, it doesn't look like it has an a value, but really we know the a value is just 1. Yeah? So the a values are the exact same. Therefore, they're going to have the exact same step pattern. But the only difference here is that this one has a -2. And if you look closely, the original y equals x squared, the vertex went down 2 spots. Yeah? Now, before we even talk about or creating a table of values for this one, can someone maybe estimate or make a hypothesis about what's going to happen to this vertex? What do you think? Take a guess. Yeah, Sam. It's going to be all the way at +8? Okay. And then what about the step pattern? What do you think is going to happen? It's going to decrease. And is it going to be multiplied by anything? Oh, okay. Okay. Wow. You guys are good. So let's go ahead and let's make a table of values for this one. Y equals -2 something squared plus 8. And again, this is where pulling out a calculator is super helpful. I'm going to do -2 bracket -3 close bracket squared plus 8. -10. And then I can just go back into my calculator, replace -3 with -2, and then I know I get 0 here. Anyone else get 0? Replace -2 with -1, 6. And at 0, I guess we should get just 8. And then +1. Oh yeah, and at this point, you might see a pattern. Not 21, just 2. I'm just going to double check that 3. Yeah. Okay. Well, let's graph this one. I'm going to do this one in blue. So -3, -10. Okay, great. Got it. -2, 0. Okay. -1, +6. All right. 0, 8. Interesting. 1, 6. Got it. 2, 0, 3, -10. Move this garbage over here. And there you have it. You can almost see it drawing a smooth curve. That's all right. That's not bad. There you have it. Starting at the vertex, calculate the step pattern. Okay. Over 1, down 2. Over 1, down 1, 2, 3, 4, 5, 6. Okay. Over 1, down 10. So the step pattern here is -2, -6, -10. And are we surprised by that? Maybe not. After the homework yesterday, you're not too surprised by that. Because what do you notice from the original step pattern of y equals x squared, which we know is 1, 3, 5, and our new step pattern of -2, -6, -10. What do you notice? Yeah, it's multiplied by -2. It's -2 times as big or is it small? Because it's -2. It's multiplied by -2. I like that. What do you notice from the original vertex of y equals x squared, which we know is 0, 0. Yeah, the vertex here is 0, 0. And our vertex, which is now 0, 0, 8. Is that what our vertex is? 0, 8, right up here. What do we notice? Well, it just looks like it went up 8 spots. It went up 8. So now that you have a great idea of what that A value does, yeah? Up, down, skinny, narrow or wide. What do you think that this constant term might do to the parabola? What do you think, Kent? Pardon me? It is the y-intercept, absolutely. But what's actually happening to the vertex? Because when this was -2, look where our vertex is. Yeah? When it was +8, look where our vertex is. So what do you think? It kind of determines the vertex. Yeah, I think I agree with that. So what I want us to do is really look at this. What I have here is I have these graphed on Desmos, ready to rock. So we have, first of all, we have y equals x squared, which is lovely. So the a value in y equals x squared, what's our a value here? Is it just 1? I mean, it doesn't look like it's any a value, but really we know there's a 1 there. Direction of opening, because a is positive, and because we see the graph, we know this thing opens up. The vertex is just 0, 0. Yeah, I'm going to put a v beside the coordinate. And, oh yeah, remember this word? The axis of symmetry. Do you remember that? What's the equation of the axis of symmetry of the graph y equals x squared? What is it? It is. Now, because we can see the graph, what do you think the axis of symmetry is? What do you think, Ken? Yeah, it's x equals 0. And a lot of us got the idea that, oh, it's just the x part of the vertex. Remember that? Okay. Now we're going to graph y equals 2x squared. I'm going to leave y equals x squared there. Here's y equals 2x squared. Interesting. So what's the a value here? 2, thank you. And is it opening up or down, the blue one? It's opening up, absolutely. What's the vertex? The vertex is 0, 0, I agree. And then the axis of symmetry would just also be x equals 0. Okay, now, 0.5 x squared. What's the a value here? 0.5 or 1/2, same idea. And let's graph this thing. Or what do you think? Is it opening up or down? It's opening up for sure. It's the green one here. We know it's opening up because it's positive. What's the vertex of this one? 0, 0, absolutely. And then that must mean that the axis of symmetry is also x equals 0. And look how narrow it is compared to y equals 2x squared. Now the red one there is y equals x squared. Yeah. When it's 2x squared, it's more narrow, or stretched, we might say. And when it's a fraction, like 0.5, it's much more wider, or compressed, we might say. Now, for the last two, negative 2x squared. What's the a value here? Negative 2, absolutely. Is this going to be opening up or down? What do you think? Down. Why down? Because it's negative. And where do you think the vertex is going to lie? 0, 0. Okay. And then the axis of symmetry must also be x equals 0. Let's have a look at what this looks like here. There it is. So because it's now opening down, some people might say that, oh, this one, it was reflected on the x-axis, which is true, but also, opening down is just as good, but reflected on the x-axis is what you might hear a lot of. And how about this last one here? Negative 0.5 is the a value. This one's for sure going to be opening down because you guys are pros. 0, 0, of course, because any quadratic in this form has a vertex of 0, 0. And the axis of symmetry is also x equals 0. Yeah? So what can we conclude about the a value? Well, the graph of any, quadratic, y equals ax squared, is the same as y equals x squared after either a vertical stretch or compression, yeah? Stretches meaning like +2 or -2, that's a stretch, because it's a big whole number. But when it's a fraction between 0 and 1, then it would be a compression. So maybe we could even write a little note of that here. Vertical stretch, like a number, or a compression, we could say a fraction. I like that. Vertical stretch is if A is greater than 1, and then a vertical compression is, now that just means, greater than 0 but less than 1. So basically this just means the fraction. So basically a number or a fraction. And one more thing, because that A value could be positive or it also could be negative. And what that does is we say, okay, well, it's a reflection in the x-axis if A is less than 0, or if it's negative. It could be negative anything. And we learned that. Negative 0.5 is still facing down. -2, A value is still facing down. Now at this point, you might not be too shocked by this, but I need you to stay with me. We're not only talking about the A value today, we will talk about the rest of the transformations that might occur. So I'll give you a moment to write that down. Yeah, notice the wall here. We're getting another whiteboard, I hope. That's the plan anyway. Okay, more time? Good. Now, what about this value here? So I know in the past, we really put an emphasis on y equals ax squared plus bx plus c. And we called that standard form. And it's still good, don't get me wrong. We also kind of learned about x minus s, this form here. And it's called factored form. And it's lovely, don't get me wrong. We love factored form. But we're headed towards a new form of quadratics, which is top tier. It's really, really, really good. And this last term is now called k. Yeah. So we're going to investigate what this value of k does. So basically, it's that number that's at the end here. And we talked about it a little bit. We graphed it, made a table of values. So let's go ahead and investigate this using Desmos. So y equals x squared. The value of k here, well, I guess it would be plus 0. We don't actually write that. So the k value here would be 0. The direction of opening would be up, of course. The vertex we know is 0, 0. And then the axis of symmetry would be x equals 0. It's right on this y-axis. So we say x equals 0. Now, y equals x squared plus 2. Here's what this looks like on a graph. It's the blue one there. Notice that it just went up 2 spots. That's all that happened. It just went up 2 spots. So the value of k here would be 2. It's still opening upward. You can see the blue one there. The vertex is now changed. It's 0, 2. Yeah? And then the axis of symmetry is still x equals 0. So at this point, you probably understand what's going on. Value of k is 4. Direction of opening is up. Yeah? What do you think the vertex of this one would be? This third one. X squared plus 4. No clue? 0, 4. Absolutely. 0, 4. and then the axis of symmetry still x equals 0. So what we can kind of accumulate from this is if we just put a k value in here, yeah, if k is 1, where's my quadratic? Oh, I haven't written it up. Okay. So here's when k is 0, right there. Now, when k increases in value, the quadratic goes up. You know, see that vertex? That vertex is going up, 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 up. But when k decreases in value, it's just going down. Now, the step pattern's remaining the same. Yeah, a value is still 1. But all that's happening is this quadratic is moving like that. It's that vertex that is moving. Or Ken makes a good note and says, well, it's also the y-intercept. Yeah, it is. It's very true. So that's what this k value does, up and down. So with that logic, x squared minus 1. The value of k, for sure, is negative 1. We know this thing is opening up still because the a value is still 1 here, yes? The vertex would now be 0, negative 1. And the axis of symmetry is still x equals 0 because all we've done is moved up and down. We have not moved left or right yet. And lastly, k value here is negative 3. Of course, this one is opening up, and this vertex is 0, negative 3, and the axis of symmetry is x equals 0. So what can we conclude? We can conclude that the value, oh, it says q in here. That should not say q. This is k. K is basically what we say a vertical shift. And that's the terminology we got to get used to using. And it's either up or it's down. It's a vertical shift up if that k value is greater than 0. Or basically, we could just say if it's positive, greater than 0 is lovely. But really what we're talking about here is just if it's positive. And it's a vertical shift down if k is less than 0, and really what they mean there is if k is negative. And that k value is super, super useful. You are going to see. I'll give you a moment to write this down. Good? No? Apologize for this penmanship here. Writing with a nose. Questions so far? Pretty good? Okay. Now, let's have a look here. Properties of the quadratics, y equals ax squared plus, suppose we should say, okay. This last term here, yeah? We know in standard form we called it c, yes? So when this a value is positive, the vertex is going to be 0 and whatever that c value is, that last term. Or we should change this to k. We want k here. And that a value is positive. Well, axis of symmetry is always x equals 0. We know it's going to always be opening up. And the step pattern, well, it's going to be whatever 1, 3, 5 multiplied by the a value is. So we'll say like 1a, 3a, 5a. So if a, for example, was negative 2, we would multiply 1, 3, and 5 by negative 2. If the step pattern was 1/2, we would multiply the step pattern here. We'll sub in 1/2 for a. Now, here's the difference. When we have negative a x squared, we know that vertex is still going to be 0, comma, whatever that last term is, 0, comma, k. The axis of symmetry is still x equals 0. Now, this thing opens down because the a value is negative, and the step pattern, it's still whatever that a value is. We're going to multiply 1, 3, and 5, or you can even go on, but I think 1, 3, 5 is enough. Multiplying by whatever that a value is. So, what we're going to do now, this is very similar to yesterday, except the vertex has now changed a little bit, yeah? It was always 0, 0 yesterday. Now it's a little bit different. In this first one, we'll do this one in red. What's our vertex of this quadratic? Yeah, 0, negative 7. And we know it's that negative 7. It's right there. It's not 0, 0. It's actually down 7 from there. So we'll say 0, negative 7. Now, what about our step pattern? I'm going to put a little title here, step pattern. Well, we do know the step pattern is 1a, 3a, 5a, dot, dot, like it does go on, but I think 1, 3, and 5 is enough. And we're going to multiply each of these by 0.5. We're subbing in the a value of 0.5. This here is our a value. So the new step pattern is 0.5, 1.5, 2.5. So when we graph these, we're going to start at the vertex, which is 0, negative 7, just right there. And from the vertex, we're going to go over 1, up 0.5. Okay? And then from this point, over 1 and up 1.5. So there's a half, and then there's a whole 1, 1.5. Lovely. And then from this point, over 1 and up 2.5. 1, 2.5. And that's, I think, enough points on that arm there. And the same idea occurs on the other side here. Over 1, up 1/2. Over 1, up 1.5. Over 1, up 2.5. And we get this quadratic. We should try to draw in our smooth curve here as best we can. And maybe even label it and say, all right, this one is y equals 0.5x squared minus 7, the red one. Now the blue one, what's the vertex here? What is our vertex of this next one? Ooh. 0, comma, positive 10, yes. Now our step pattern. Our a value, well, our step pattern is 1a, 3a, 5a, dot, dot, dot. What's our a value here? Negative 3. So we're going to sub in negative 3 into each of these. Whoa. What happened to that 3? There you go. And when we simplify this, we get something like negative 3, negative 9, negative 15. Now, for whatever reason, just be careful. You know, everything in my head told me negative 6. I don't know why, but just be cautious of that. So we're going to start at 0, positive 10, up there. And our first step is over 1, down 3. 1, 2, 3. Great. From this point, over 1 and down 9. So that's down 7 and then 8, 9. And I don't even think we can go over 1 and down 15. That would be way down on the floor here. So that might be just enough points. 7, 8, 9. Great. We draw in our smooth curve. And this is y equals negative 3x squared plus 10. So far, so good. If I were to give you one of these, would you be able to graph these with confidence? Yeah? Give me some. Give me a head nod or one of those or one of these. Yeah, pretty much. Good. Okay. Questions about anything? Okay, this is good. What did I do? Oh, I hit this button. Okay, now, look at this one. What about the horizontal shift? Like, we know the vertical shift up and down. We know the A value, yeah? What about moving left and right? Can that even happen? Well, let's first graph this right here. Y equals x plus 2, all in brackets, squared, plus 3, using a table of values. And this is where a calculator really comes in handy. Now, what we're really doing here is we're going, okay, y equals, x, which is -2, plus 2 squared plus 3. And we're looking at the result of this to just be 3. Okay? So we're doing that for every single x value here. So -1 plus 2, close the bracket, squared plus 3. And I get 4 for here. We sub in 0. 0 plus 2 squared is 4, plus 3 should be 7. Sub in 1. 1 plus 2 is 3, squared is 9, plus 3 is 12. Sub in positive 2, we get 2 plus 2 is 4, 4 squared is 16, plus 3 is 19. So these kind of become our coordinates. Okay, first one, -2, positive 3. 1, 2, 3. Are these lines as faint on yours as they are on mine? They're not there. Oh, there's no lines at all. Interesting. -1, positive 4. Okay, 0, 7, 0, 7. 1, 12. 2, 19. Tough. This looks like it's one side of the quadratic here. Yeah? Let's go on Desmos and really look at this thing. We got y equals x plus 2 squared plus 3. Okay. Notice over here, -2 comma 3. That's our new vertex. So what's the step pattern here? Looks like we go over 1, up 1. Yeah? Over 1, up 1, 2, 3. So our step pattern is probably looking like 1, 3, 5. And we don't have this other half here, but we can kind of sketch that in here. Our step pattern here, over 1, up 1, over 1, up 3, over 1, up 5. Our step pattern, 1, 3, and 5. Our vertex, get a better picture of this thing. Our vertex is -2, positive 3. Now, how is this equation related to the coordinates of the vertex? Because if you think about it, this plus 3, we're not too shocked by the plus 3, right? We know it went up 3, this vertex. But what about this -2? See in here? See how it says plus 2? But our vertex says minus 2. That's interesting. The plus 3 to the value of the vertex, it makes it go up 3. Yes? What is the plus 3? Up 3 units. What is the plus 2 due to the x value? Well, for some reason it went left 2 units. Now, what about the y-intercept? The y-intercept is 7. Oh, sorry. The y-intercept is 7. This right here is no longer the y-intercept. That's the new y part of the vertex. But if we did want the y-intercept, what we'd have to do is get this thing into standard form. Because we know in standard form, ax squared plus bx plus c, that c value is the y-intercept. Yeah? So how do you think we're going to change this into standard form? Does anyone have any ideas? Maybe not. Well, what we're going to have to do is we're going to have to yeah. Yeah. What you can do is plug in x equals 0 and solve for the y-intercept. Yeah? I love that. Set x equal to 0. You could do this for sure. Y equals. Instead of x, we're going to say 0 plus 2 squared plus 3. Okay. Y equals 2 squared plus 3, which is 4 plus 3, which is 7. Love that. Setting x to 0 in any function, linear or quadratic, will certainly give you the y-intercept. Now, if you wanted this in standard form, you could just expand this. Yeah, x plus 2 squared. So really that's x plus 2 times x plus 2. And we know that we can multiply two binomials by using FOIL. And we get like x squared plus 2x plus 2x plus 4 and plus that 3 that we haven't done anything with. We can collect the two x terms, and we can also collect the two constant terms, and we can get x squared plus 4x plus 7. And there it is, at plus 7. But this is just as good. I love that. Okay. This term in the bracket here, that number that appears in the bracket is called h. We refer to this thing as h. So the weird thing about h is that in this form, it says x minus h. And that's a little weird. So we know the graph of y equals x squared. We know the value of h, well, it has to be 0. There's nothing there. We know this opens up. Lovely. We know the vertex here is 0, 0. And this axis of symmetry is x equals 0. Now, x minus 2 squared. This is almost like a trick question, but what is the value of h? Be careful when you answer. What do you think? Now, why do you say positive 2? Yeah. It looks like it says negative 2 in the brackets, doesn't it? It looks like it says negative 2. I agree. But the equation says, well, whatever h is, we're subtracting h. So that would be we're subtracting a positive 2. So really, this h value is positive 2. So let's graph this thing and see what it looks like. X minus 2 squared, right here. And look, that H value is positive 2. And we shouldn't be surprised that we went from 0, 0, 2 units to the right, towards the positive guys. Yeah? So what can we say about this? Well, the direction of opening is certainly still up. What's the vertex here? Now the vertex is 2, 0. And if that's the case, and the axis of symmetry is usually the x part of the vertex, what you can see on the graph is that the axis of symmetry is no longer x equals 0, it's x equals 2. Now the same thing might occur for y equals x minus 4 squared. There it is. And you shouldn't be too shocked by that. Yeah, we just saw what minus 2 did. Now let's look at x minus 4. What's the h value here? Positive 4. Yes, that's so important. I know it looks, x minus 4 looks like negative 4. But really it's a positive 4 that's in there. It's opening upward. The vertex is 4, 0. And the axis of symmetry is x equals 4. Now, what's going to happen when we do x plus 2 squared? X plus 2 squared. Well, have a look. It went over minus 2. It went to the left 2. What's our h value here then, if that's the case? How do you know that it's negative 2? Oh, that's interesting. 2 negatives make a positive. So really what happened in this problem was they said, okay, y equals, x minus, and then they said minus negative 2, close bracket, squared. Now math people will not leave it like that ever, because that's not fully simplified. It says here x minus negative 2. So what do these math people do? They say, okay, well, this is really just x plus 2 squared. So I know it looks like it should be a positive 2 here, but really, because of that double negative that's occurring inside of the brackets right here, it's really a negative 2. And that's why, well, we open up for sure, and that's why we move to the left 2. We go towards the negative ones. Yeah? The vertex now would be negative 2 comma 0, and the axis of symmetry is x equals negative 2. In this last one here, by that logic, we know that the the h value is negative 4. This one still opens up. The vertex would be negative 4, 0, and the axis of symmetry is x equals negative 4. Yeah? Now, to conclude this h value, h controls the horizontal shift. And just like vertical shift, horizontal shift is the terminology we want to use. And it can either go right or it can go left, because those are the horizontal movements. But this one is a little bit tricky. You almost want to put maybe a few examples. That's what I tried to do in this note here, is provide a few examples. Show you what I mean. Now, a horizontal shift to the right is when that value of h is greater than 0, meaning that value of h is positive. Go to the right, we go towards the positive side. Now, what it looks like, oddly enough, is in the brackets, it'll look like x minus 2 squared. And that's a little weird, because a lot of us think, okay, x minus 2 means negative 2. But really, according to this, we know that this is a positive 2 in the brackets. And we're subtracting the positive 2. So I would for sure put this, yes, Will. No, the k is outside of the bracket at the end there. Well, the h is inside of the bracket. It's all going to come together in the next one. You'll see. The equation of the axis of symmetry is always going to be x equals whatever that h value is. Yeah? And of course, this thing can move left when h is less than 0, meaning when h is negative, but it's going to look positive in the brackets because of the double negative that's occurring. So again, even here, it's really y equals x minus negative 2 squared. And that that minus negative 2 is the reason why we get a positive. Okay, I know. It's almost like information overload. Completely agreed. But I feel like I had to show you each piece of this individually before we all kind of brought it together. We saw the A value a little bit yesterday. We saw it again today. We learned about H. We learned about K. So all these variables kind of come together in a particular way to create a whole new form of expressing quadratics. And we call this form the vertex form. Vertex form. And this is the best page, I think, because it tells you everything you're going to need to know. You don't have to write anything down. I just want you to have a look here. First of all, if there's ever a number out front of here, it's the A value. And we know what the A value does, right? The A value is actually the same in standard form. It's the same in factored form, and it's the same in vertex form. That A value is consistent among all three of the forms. What's beautiful about this one is that we get the vertex right away. Look at that. HK is the vertex right there. So it's like, oh, what's the vertex of this one? Boom. No more solving for any vertexes. Like factoring, x-intercepts, axis symmetry, sub it into the equation. None more of that. Vertex can be yoinked right out of this thing. Once you have the vertex, you already have so much information, right? Like the other unit, past couple units, we've been dying to have this vertex because it tells us the max min value, yeah, optimal value. It also tells us the axis of symmetry. So, vertex number one. Now, if we're talking about translations or transformations, basically movements of quadratics compared to y equals x squared. This h value, yeah, it's the horizontal shift left or right, yeah? But be careful, because if it says x minus 2, we know that's 2 to the right, because it's really a positive 2. And if it says x plus 3, we know that's 3 to the left. It's really a minus 3 that's in there, because of the double negative thing. But the k value is very straight up. It doesn't lie to us. If it says plus 2, it means up 2. If it says minus 5, it means down 5. The k value is really nice guy. H in here, and he likes to play a little bit of tricks. So be careful of this one, all right? One last thing, the A value. If it's positive, opens up, negative, opens down. And that's it. Like, I know this lesson dragged, it went on, but I had to show you each letter and what they do before we bring it all together. Now watch how good you already are at this sort of stuff. So let's not forget, I'm going to write it on the chalkboard. The whiteboard. Y equals A bracket x minus h close bracket squared plus k. Our job is to look at these quadratics here that are in vertex form, and we want to tell whoever it is up here asking the questions, I guess me, that what happened to y equals x squared. So it says describe the transformations that were applied to the graph of y equals x squared. So let's pretend we started off with y equals x squared, and we ended up with this disaster here. And someone's like, well, what happened? What happened? What did you do to this thing? Well, I guess we could say this. The first thing that we did is that this right here, this A value. How can we use the nerdiest language possible to kind of explain what the A value of 2 really did to this quadratic y equals x squared? Well, we could say there was a vertical stretch by a factor of 2. And that's what that A value did. A value, and because it's a whole number and not a fraction, it becomes a vertical stretch by a factor of 2. Let's look at this 3 in here. Now here we go. Got to be extremely careful with the 1 in the bracket. Just like when we're factoring, right? It's like x minus 4 really means x equals positive 4. Same idea. Just be careful here. This 3, what type of shift was it? Was it horizontal, left and right? Or was it vertical, up and down? Horizontal. Now, the hardest part here is thinking about this. X minus 3. Is that 3 positive or is that 3 negative? It's positive. So because it's positive, and because it's a horizontal shift, what happened? What can we say? It went to the right 3 units. So we'll say horizontal shift 3 units, or I guess we should say to the right 3 units. To the right 3. And it's important. Just like we knew it was a vertical stretch by a factor of 2 because the 2 is a whole number, we know that this shift is to the right because it's x minus 3, which we know really is a positive 3 in there. And this last one here, right, our favorite one, the k value, very straight up person, right? Does not lie to us. K value is plus 4. So we can say vertical shift up. And we know it's up because it's positive 4 units. Not too shabby, no? Pretty good. Now, here we are. Y equals negative 0.5. X plus 5 squared minus 7. Whoa. The first thing that we're going to talk about here is just the little negative right there. That little negative. What does that negative do to y equals x squared? Y equals x squared right now, after the negative. Yeah? What can we say? Okay, I know. It's now opening down. Sure. But really what they want us to say is it was a reflection on the x-axis. Yeah? So we can say vertical reflection on the x-axis. That's just that little negative there. And how about 0.5? It's either going to be a stretch or compression. What do you think it is? What do you think? Yeah, how come? Yeah. It's between 0 and 1, yes. Vertical compression we'll say by a factor of 0.5 or 1/2, whatever that might be. Now in the brackets there, x plus 5. Be careful. Horizontal shift, we know it's a left or right. But which one is it? Is it left? Or is it right? It's left. How come? Yeah, it's technically negative 5. And lastly, it's almost like you get 10 of these. You're like, oh, okay, thank you. You know, this minus 7 here. It is a vertical shift down. We know it's down because it's negative 7. We'll say down 7 units. Okay, great. Now they want us to match the graphs to the equations. That's example 5, that's just beneath here. Match the graph to the equations. Now, this can be a little bit tricky. You got to be very, very cautious. The beautiful thing about this new form called vertex form is that you can pull out the vertex almost immediately, and based on the A value, you know whether it's opening up or whether it's opening down. So this first one here, yeah, we know it's opening down because that A value here is negative. And then the vertex is going to be, well, I guess positive 4, yeah, because it says x minus 4. We know it's a positive 4 and positive 5. So what we're going to do is when we look at the graph, we're looking at which parabolas are facing down, and there's only 2 of them here, and then which one has a vertex of 4, 5. 4, 5 facing down. We know for sure this one is A. Yeah? Part B, this parabola. It's got an A value of positive 5. We know it's opening up, and we know it's super narrow. And the vertex here is negative 1, negative 5. I know, x plus 1. I know. Negative 1, negative 5. So negative 1, negative 5, super narrow, opening up. That's got to be it. B. Part C. There's nothing out front of the bracket. We assume it's a positive because it's not negative. So we know this is opening up. And then the vertex here is, well, it says x plus 6 squared. So maybe negative 6, comma, and there's nothing at the end here. So we assume that it's just 0. Yeah? So opening up, negative 6, comma, 0. Here it is. This must be C. How about this one? Well, I mean, there's only 2. One's facing down, one's facing up. You can almost kind of do it. But just for funsies, this one's going down. The vertex is negative 8, positive 1. So negative 8, positive 1. This has to be D. And of course, the last one is E. But always check the last one. This is opening up. The vertex is 7, comma, 3. Opening up, 7, 3. There it is. And that should be E. Okay? It's almost like you're vertex hunting in there. You could have gone without checking whether it's up or down, but I would always double check up or down. Because if they did have the same vertex, one was up, one was down, then you'd have to kind of know here. Questions about this? Right? See how it all comes together so nicely? It's not. Okay. Write the equation for a parabola that satisfies the following conditions. Okay. So it's almost like this first one here, up here, but going the other way. They'll tell us the stuff that we just did here, and we got to come up with the quadratic. So, vertically stretched by a factor of 6. Okay. Reflected in the x-axis. All right. And then shifted 7 units left. Okay. So we do know that it's y equals a x minus h squared plus k. That's what we're dealing with. So, vertically stretched by a factor of 6, what letter does that affect? A, x, h, or k? A. So we know the A is going to have a 6 in it, for sure. Got it. Now it says here reflected in the x-axis. What letter does that affect? Meaning, yeah. X? Well, it means that it's facing down, right? It's from smiling to frowning. Yeah, it's going to be A. A again. So it's going to be really a negative 6. And then shifted 7 units to the left. So 7 units to the left. So the horizontal shift, I think, is H. So we know that H will be, or I'll put that over here. Okay. H is going to be negative 7 because it was left 7. So what we get is y equals negative 6 bracket x minus negative 7 squared, and then there was no vertical anything, so I suppose you could say plus 0 if you wanted to. Not necessary, but it didn't really move. But what we do want to do is simplify this minus negative 7. We'll get negative 6 x plus 7 squared, and I suppose plus 0. I know there wasn't really any k value influence here. There was no vertical shift. Okay, in the grand finale, putting all of this together, we're going to be able to graph quadratics that are in vertex form. And again, what we need, two things. One is the vertex. Two is the step pattern. So, what is the vertex of this quadratic? Now, I know, it says minus 6, but really we know that means what? Yeah, positive 6, negative 9. We can almost go to the graph and say positive 6, negative 9. That's our vertex. Now, the step pattern. It's 1A, 3A, 5A. What's our A value? It's 3. So 1 times 3, 3 times 3, and 5 times 3. We got 3, 9, and 15. So from this vertex, we're going to go over 1, up 3. Yeah, over 1, up 3. I like to even draw these in. Over 1, up 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't think we can do that third one there. Over 1, up 3. Over 1, up 9. And there we have it. This is our parabola. Okay, part B. What is our vertex? Yeah, negative 5, positive 6. I know, we got to be very careful with these guys in here. Step pattern. 1A, 3A, 5A. Our A value is that negative 4. So we're going to multiply each step by negative 4. And our pattern is negative 4, negative 12, negative 20. So we're starting at negative 5, positive 6. We're going over 1, down 4. 1, 2, 3, 4. Over 1, down 12. Which brings us all the way down here. Yeah, that was a huge vertical stretch. Over 1, down, over 1, down. There we have it. You might need some graph paper here because we are going to be graphing some of these in vertex form. But our homework is down here on 262 and 269. Where's my textbook? Yeah. I know it looks like an absurd amount, but it'll go fast. It will.